In the last lecture, we looked at radiative transfer in the Earth's atmosphere. And we started with a very simple model of the Earth without atmosphere, and we saw that the solar radiation coming from the sun, that multiplied by the cross sectional area of the Earth times the radiation absorbed, where alpha is the reflectivity, can be equated to the radiation emitted by the Earth atmosphere system and into the surface area of the Earth. So, in this model, if we took as the measured value as 136 watts per meter squared, and the Earth's reflectivity to radiation from the sun, also called albedo, if it is taken to be 0.3 or 30%, then the radius of the Earth is not relevant, it cancels out. We have a simple expression of S by 4 into 1 minus alpha equal sigma T e to the power of 4, and if you calculate the effective temperature of the Earth, it will come out as 255 degrees Kelvin. This is not the surface temperature of the Earth, but the effective temperature of the atmosphere system, which has to radiate at a black body temperature of 255 degrees Kelvin, so that it can essentially get rid of the radiation absorbed from the sun. The radiation absorbed from the sun is nothing but 1365 by 4 into 0.7, and this comes close to 239 watts per meter squared, and a black body at 255 will emit this radiation. But our real interest was not in the effective black body temperature of the Earth, but the surface temperature. Now, the effective black body temperature of 255 Kelvin will also be the surface temperature if there was no atmosphere. So, if there is no atmosphere on Earth, then Ts is equal to T, if the Earth behaves like a black body. But we would like to know the temperature of Earth with the atmosphere. So, for that we consider a very simple model having a one layer atmosphere, and we have the sun's radiation coming here S by 4 as solar constant, and by division by 4 is because the cross sectional area of the Earth is 1/4 the surface area of the Earth, and we assume that S by 4 into 1 minus alpha is the energy reflected, and A is the radiation absorbed from the sun by the atmosphere. So, what reaches Earth's surface was S by 4 into 1 minus alpha minus A, that reaches Earth's surface. We neglected all other methods of heat transfer except radiation, that we neglected the heat loss from the Earth's surface by evaporation and by sensible heat flux. So, that is a very unrealistic approximation, but we did that because we wanted a purely radiative heat balance. And then we assumed that the Earth's atmosphere emits equally up and down, and based on this simple model, we showed that the temperature of the Earth can be estimated to be So, although this model is not very accurate, it is still a very good model to explain the role played by various radiative properties on Earth's climate, that is, how the various radiative properties of the atmosphere control the temperature of the surface of the Earth. For example, S is the incoming radiation. If it goes up, it will obviously increase the Earth's surface temperature. Alpha is albedo, or the reflectivity of the Earth to solar radiation, and if that goes up, obviously temperature will go down. Similarly, if the solar absorptivity of the atmosphere goes up, it will reduce the radiation coming to the Earth's surface, the temperature surface will go down. And finally, the emissivity of the atmosphere. So, if this goes up, temperature will go down. So, this is brought out very nicely by the Sibyl model, that increase in albedo and solar absorption of the atmosphere brings down the Earth's temperature, while increasing the surface emissivity will increase the surface temperature. Now, let us look at how this model reproduces the observed temperature. We saw in the last lecture that if we assume the alpha to be 0.3, which is the observed value from satellite, and the solar absorptivity to be around 0.2, and emissivity of the atmosphere to be 0.95, then the surface temperature of Earth can be calculated from the formula we just wrote down to be 287.7 Kelvin, which is very close to the observed temperature of the Earth's surface. But let us see how sensitive the result is to the choice of emissivity, because we do not know this quantity accurately. Suppose the emissivity was 1, not 0.95, then temperature goes up to 291.5. So, it goes up by around 4 degrees. For a change in emissivity from 0.95 to 0.95 to 1, that is, a change in emissivity of 0.05 increases the temperature by almost 3.8 degrees Kelvin. So, this shows how sensitive the Earth's temperature is to the emissivity of atmosphere. And just to complete the picture, we give one more value between take a value of 0.9, we go 0.05 below, then the temperature is 283.9. So, we see that if the emissivity increase here, so the emissivity decreases by 0.05, then the surface temperature decreases by around 3.8 Kelvin. So, it is quite symmetric, that is not surprising. So, the main message is a small change in emissivity of the atmosphere causes a large change in the temperature of the Earth. So, for example, in the last 100 years, 120 years, temperature of the Earth has gone up above 1 degree Kelvin. So, that could have been caused by just a change in emissivity of the order of 0.01. That is a very small change, and we are not in a position to measure the emissivity of the atmosphere to that accuracy. Secondly, the concept of emissivity itself is a bit difficult to calculate, because the temperature of the Earth's atmosphere is not uniform. The Earth's surface may be at 287.7, but the temperature decreases height until you go to tropopause, and then it changes. So, when you are going to define emissivity, You remember emissivity is nothing but emission by surface divided by emission by a black body at this temperature. If you are concerned with Earth's surface, that is okay, we know the temperature. But when you are trying to define the emissivity of the atmosphere, you are talking about atmospheric emission divided by sigma T to the power of 4, but the TA is varying between 287.7 and to around 200 Kelvin by the time you reach the tropopause. So, which temperature do we take? That is not quite obvious. So, it is very difficult to highlight. The second point, which is more important than this, is the fact that in our simple model we assumed that the atmosphere emits equally upwards and downwards. This is a very poor approximation. This is all right if atmosphere is a thin layer at constant temperature Ta, but the real atmosphere is a thick layer whose temperature varies between 287.7 to 200 over a thickness of around 10 to 15 kilometers. So, this simple model is totally invalid, and the reason why it should be quite obvious. Again, we will write the temperature profile of the atmosphere of the tropopause, let us say is around 200 K, and this is around let us say 288 K for convenience, round numbers. Now, this layer, when it emits radiation upwards, most of the emission will come from this region, because the radiation emitted by surface will be absorbed by the gases next to the surface and they will re-emit radiation. So, what you will observe from the top of the atmosphere is the radiation emitted by the upper layers. On the other hand, when you look at radiation downwards, this is mostly emitted by layers here near the Earth's surface, because radiation emitted by layers above there are absorbed by the gases in the lower layer and re-emitted. So, that the radiation coming from going above comes from layers in the upper region, while the radiation coming downwards is from layers which are at a higher temperature. So, we expect that this quantity, the downward emission, will be much larger than the upward emission. Okay. Because the downward emission comes from layers of the atmosphere closer to Earth's surface at a higher temperature, while the upward emission will come from layers in the upper troposphere which are low temperature. So, this is a basic flaw in this model, but remember the other major flaw was our neglect of evaporative heat loss and sensible heat loss from the Earth's surface. The Earth, to maintain its temperature around 288 Kelvin, is cooled both by radiation as well as by convection, and the convection comes in two forms: the dry convection, which is sensible heat flux, and evaporation, which is occurring over the oceans. We ignored that term and we allowed the Earth to radiate purely like a black body. So, there are two major flaws, and let us see what do observations say about these fluxes. So, let us look at the Earth's surface, the top of the atmosphere, and see what are the typical observed fluxes. Now, from satellite we know that radiation coming per unit area of the Earth's surface is 342 watts per meter square. That we know very well, because this is measured by satellite and measurements have been going on for the last 30 years, and they have been averaged very carefully, and there is absolutely no doubt that the incoming radiation, although there is variation, small amount of variation, but by and large this quantity is well understood. Similarly, we also know how much energy is reflected, that is around 107 watts per meter square. About 1/3, not 1/3, 30% of the incoming radiation is reflected back to space. So, the difference between these two is the radiation absorbed, which is 235. So, for the earth to be in steady state, it must emit 235. So, that is very clear. So, from the top of the atmosphere, we are very sure that the total radiation absorbed from the sun by the earth atmosphere system is 235 watts per meter squared, and the earth atmosphere system has to radiate in the infrared amount equal to 235 for the earth to be in steady state. So, this is fairly well established by satellite measurements of both the reflected solar radiation, the incoming solar radiation, and the emitted flux. So, this is the emitted long wave flux. These are short wave flux on this side. So, all these are measured accurately at the top of the atmosphere. So, we know the balance precisely. Now, we come to the earth's surface. Earth's surface, the quantities are not so well known, but a lot of modeling exercise has been done, and we know that on an average radiation from the sun is around 168 watts per meter square. This much is coming in from the sun, average all day and night and all seasons, global mean. We also know that roughly the evaporative flux is 78 watts per meter square. This is not as accurately known as radiation, because this must be estimated by approximate formulae, and the heat loss by dry heat transfer, so called sensible heat flux, around 24. So, sum together this is about 102 watts per meter square. So, 168 watts per meter square is coming to the surface from the sun, and about 102 is lost by the earth's surface by non-radiative process, that is evaporation and dry transfer. And since we know the temperature of earth to be 288, we know that as a black body we assume it must emit 390 watts per meter squared. So, in order for it to lose only 6, remember the difference these two is 66 watts, it must only be receiving back from the atmosphere 324 watts per meter square. So, the earth's surface radiates 390 watts per meter squared, of which most of it comes back from the gases such as carbon dioxide, water vapor, methane, ozone. They all radiate back 324. The net is 66, and which is the, so the incoming radiation 168, outgoing non-radiative is 102, radiative outgoing is 66, and we have a balance. Okay. But the key point about this tabulation is, notice that the earth atmosphere emits to space 235 upwards, but emits back to the earth 324. So, this is the point which clearly shows that the upward and downward flux of radiation from the atmosphere are not equal. They are highly unequal, and this was ignored in our simple model, but we do not have much choice in this case, because the simple model can only assume that simple model assumes that atmosphere is a thin plate at a single temperature Ta, and hence it has to emit equal direction, but reality is of course we can of course slightly improve the model by assuming atmosphere and a stratosphere. So, 2-layer model can be postulated. It will slightly improve the situation, but still this is not going to give you a very accurate estimate. And the main point to recognize about such simple model is that they involve very large approximations, and hence cannot be expected to reproduce all the observed fluxes in the atmosphere. So, if you really want to solve the problem more accurately, we have to solve the radiative heat transfer problem for the full atmosphere as a continuous medium. If you treat the atmosphere as a continuous medium with continuously varying temperature, then of course the problem is fairly well posed. And the reason why we are recalling this is that we had solved such a problem earlier in the context of application to furnaces and other application, not focusing on atmosphere. So, let us now look at that problem and see whether we can use the solution we obtained for a gray gas in radiative equilibrium and see whether we can look at how the temperature varies linearly or almost linearly in the Earth's atmosphere. So, we go back to understanding temperature profile in the Earth's atmosphere under radiative equilibrium. So, temperature profile in the Earth's atmosphere in radiative equilibrium. Now, this problem is very close to the problem we solved earlier. There you consider two parallel plates, if you recall, and wrote down the full rate transfer equation, and then ask this question: what happens when del QR del x, x is the vertical coordinate we chose, is equal to 0. And just to recall those things so that it is easier to follow what I am saying now. So, we know radiated flux is equal to, if you assume the two surfaces to be black, as 2 sigma T1 to the power of 4 E3 of kappa. So, we are taking a gray gas, which we know is not a good approximation, but we will use it as a way to understand what is going on, and we do not expect accurate numerical values to emerge from this. So, this was the emission from the Earth's surface, this emission downwards. Now, in the present case, this is 0, because we are going to take an infinite atmosphere. So, at the top of the atmosphere is space, there is no radiation coming in. So, we are going to neglect this term. And to make our life simple, we are going to say call this as Ts, surface temperature. So, we have a surface, an infinite atmosphere, and so incoming radiation is 0. Then you have contribution from the two gases above and below a certain layer. So, this is what we had done. So, this is a great simplified form of the equation we had solved earlier. except we neglected the downward flux on the top of the atmosphere, because that is 0 in this present case. Then if you recall, we defined the non-dimensional radiative flux as QR by V1 minus B2. In the present case, downward flux is 0, upper flux is a black body flux. So, this comes out as QR by sigma T s power 4, that is radiative flux non-dimensionalized by the black body emission from the earth's surface, and a non-dimensional temperature phi was defined as T g to the power of 4 minus T 2 to the power of 4, T 2 is 0 in this case, that goes away, and this is by T s power of 4. This is a non-dimensional temperature. And when we wrote this form, if you recall, our Q star, the non-dimensional flux, was nothing but 2 times E3 of kappa plus 2 0 to kappa P of kappa tilde and minus 2 So, this is a problem we wanted to solve, and we invoked the kernel approximation, which is a way to take care of the directional variation, and we said E 2 of x is approximately equal to 3/4 e to the power minus T 2 x, and E 3 of x as half. So, with this approximation, we differentiate the equation twice and subtract it. So, finally, we were led with to this equation, which said d phi T kappa is equal to minus 3/4 Q star. So, we converted an integral equation to a differential equation by using the kernel approximation, and the solution to this differential equation was very simple, and since we are talking about radiative equilibrium, Q star is a constant. So, simple integration of this led to one more constant, and we argued that these two constants Q star and C is obtained by substituting this phi back in the integral equation, and then we got the following results for Q star and C was so the procedure is exactly same as previous derivation we did, except that the top of the atmosphere is at 0 degrees Kelvin, no radiation coming down, and so that has simplified some of the results a little bit. Now, we know what Q star is. Q star is the constant radiative flux through the atmosphere, and if you recall, and in the simple model we are going to look at right now, we will neglect the atmospheric solar absorption, and we are just looking at how much radiation is coming here, and this can be written as S by 4 into 1 minus alpha if you neglect solar absorption. This is the flux now which has to go back through the atmosphere and has to remain constant through this, and so Q r is nothing but S by 4 into 1 minus alpha. Okay. So, that is a simple result that we have got, and so Q star by our definition has to be S by 4 into 1 minus alpha divided by sigma T s power 4. And so, what the result of this exercise we did shows that this has to be equal to 1 by 1 plus 3/4 of kappa 0. Now, since we have done a very simple model of a gray gas, it is not easy to, what is kappa 0? If you recall, kappa 0 in this case will be equal to 0 to infinity A into dx. So, this is absorption coefficient, the gray absorbed out of atmosphere integrated from surface to the top of the atmosphere. And this quantity cannot be easily be evaluated because the real atmosphere is highly non-gray, has many absorption bands, and you have to do the entire wavelength integration, which we have circumvented by invoking the gray gas approximation. So, we are not able to tell you what exact number is, but from satellite data we know this quantity is around 239 watts per meter squared. We know from surface measurement this quantity is about 390 watts per meter squared. Okay. And therefore, since these two quantities are known as 390 and 239, so we are in a position to calculate the value of kappa 0. Okay. So, given these two values, kappa 0 can be estimated to be around 0.842, okay, just by substituting these numbers here and getting this value. Now, given this number, now we are in a position to write down the temperature profile. If you recall the derivation we had done earlier, the temperature profile, which now is nothing but T gas to the power of 4 by surface temperature, that is our non-dimensional quantity, and this we had derived already in the one of the early lectures, and that will come out to be the solution for phi. This is our phi quantity now, and K 0 we had pointed out was 0 to infinity A dx, while kappa will be 0 to x A dx. Okay. And so, if you can substitute kappa 0 we got from the last this one, we have a expression for temperature profile. Now, this temperature profile is linear in kappa, okay, but it will not be linear in x, because the absorption coefficient A can be written as mass absorption coefficient of the gases like carbon dioxide, water vapor and others combined together, multiplied by the density of the absorbing gas. Now, you must remember that this quantity may not vary much, the mass absorption coefficient, but this is a strong function of height in the atmosphere. That is because atmosphere is in hydrostatic equilibrium. So, in an atmosphere hydrostatic equilibrium, the density has to vary with height. In the simplest case of an isothermal atmosphere, we can easily show by this simple hydrostatic balance that density has to vary exponentially with height. So, if the density is going to vary exponentially with height, all the other gases which are mixed in the atmosphere with nitrogen, oxygen and argon, which are radiatively non-participating, they also will vary with height. For example, take the example of carbon dioxide. Its density will vary with height the same way as nitrogen, oxygen or argon. On the other hand, water vapor will vary somewhat differently than carbon dioxide, because water vapor is a condensable gas, while carbon dioxide is non-condensable. So, the water vapor density variation in the atmosphere depends very much upon the temperature variation. The temperature varies strongly with height. At some point, all the water vapor has to condense out. So, H is called scale height of the atmosphere, which is typically of the order of 8 kilometers, while that of water vapor will be more like 2 kilometers. So, the scale height of water vapor in the Earth's atmosphere is about 1/4 of the scale height of most other gases. Now, one more gas has a very peculiar behavior, that is ozone. Ozone cannot be represented by a simple exponential decline that we have. That is because ozone in the Earth's atmosphere decreases with height, but at some point starts increasing, and its maximum value is around 25 kilometers. Now, this peculiar behavior of ozone in the Earth's atmosphere can be attributed to the fact that ozone is actually created in the upper atmosphere due to the dissociation of oxygen when ultraviolet photons with high energy hit the oxygen molecule. They are split oxygen atoms, and this oxygen atom combines with oxygen molecule to give ozone. So, ozone is created in the upper atmosphere by the dissociation of oxygen and the chemical reaction between oxygen atom oxygen molecule to give ozone. So, ozone is very special because it is created in the upper atmosphere by ultraviolet radiation. Water vapor is special because its density variation of the height is influenced by the fact that water vapor condenses in the temperatures that we encounter in the Earth's atmosphere. All other gases like carbon dioxide, methane and many other gases, their variation is same as the variation of density of nitrogen oxygen. So, life is a little complicated, but we will right now focus only on water vapor, that being the most important absorbed in the Earth's atmosphere. So, if you go back and ask yourself what is kappa, we saw it is 0 to z, a 0 to I am using x's notation, that we stick to x, a dx, and this you want to write as 0 to x, mass absorption coefficient of the water vapor times density water vapor times dx. Okay. And if you assume density water vapor is this quantity, then we see that although the temperature is linear with kappa, it is dependent on x, the vertical space will be nonlinear because of this feature of the absorbing gases. So, the fact that absorbing gases have the density declining exponentially with height in the Earth's atmosphere implies that the relationship between temperature and the vertical coordinate will not be linear, but nonlinear. Now, why are we concerned about this? Our main interest is temperature profile. Okay. So, actually we are interested in dt d kappa. More importantly, actually we are interested in dt dx, which can be written as del t del kappa del x. And from that equation you can see that kappa is nothing but am rho wo into 1 minus e to the power of minus x by h w. So, at x goes 0, of course, kappa is 0 from the surface geometry, and as x goes to infinity, this quantity will be the kappa 0. So, given that, you can see that del t del x will be equal to del t del kappa, and del kappa del x will come out as so you are going to see the temperature gradient in the Earth's atmosphere varying exponentially with height. Okay. This will be the surface value. And let me just make sure that there has to be another SW, I am sorry, when you integrate that equation. So, now if you want to understand how the dt dx varies the height, you will recognize that it will vary exponentially with height. So, we will draw a simple sketch to indicate how temperature varies with height. Exponential decrease, and so let us see what is the temperature gradient at the surface. What is this value? So, you look at the previous expression that we had, you put x equals 0. So, that term will drop out, and so our expression will mainly depend on what is delta t delta kappa. Now, if you look at the expression for phi, it is coming out as 1/2 plus 3/4 kappa 0 minus kappa divided by 1 plus 3/4 kappa 0. So, if you calculate, and we drop this up to g for time being. So, we have 4 t cubed, let us keep it t g t kappa, that is what this is, by t s to the power of 4 and this will be equal to, on this side, minus 3/4 of . So, that is what is t g t kappa. Okay. And so, we can estimate the t g t kappa at the origin at equals 0, and this will come out as minus 3/4. We can take t s up over the top there, and 4 t g cube to the 1 plus 3/4 kappa 0. Now, we know all these numbers because we estimate kappa 0 would be around 0.84, t g at this Earth surface will be around 260, you can estimate from the expression for phi, and T s is around 288. And if you plug all these quantities into the equation, you will find, depending on what numbers you use, that dT by dx at equal 0 will be around minus 20 to minus 40 Kelvin per kilometer. Exact value depends on what numbers you use for water vapor density and absorption current and so on. But the key point you want to highlight is that under radiative equilibrium, the temperature gradient of the gas near the earth's surface is extremely large, 20 to 40 Kelvin change per kilometer, but this is not observed at all in anywhere on earth, and the temperature profile, such gradients are observed very close to the surface, maybe within a few centimeters, but once you move above that layer, what you might call a conduction layer, the temperature gradients are much weaker. Most of the observed temperature gradients are in the range of 6 to 9 Kelvin per kilometer. On the rate of 6 to 9 Kelvin per kilometer. And so, we need to understand why the temperature gradient that is actually observed in the Earth's atmosphere is much lower than what is calculated by the radiative equilibrium model. Now, one has it's very simply, if the temperature gradient is 20 Kelvin per kilometer, let us say this is 288 here and 1 kilometer above this comes to 268. Now, one can show that such a layer will not be stable. Why is that? One can easily calculate the density of the upper layer here, and so you will find the density of this layer and density of this layer, and you will find that if you take a parcel of air from the lower layer and just displace it, it will rise upwards because the density of the atmosphere goes up with height, goes down with height. So, if you take a parcel of air from the lower part of this layer, 1 kilometer layer, and you lift it, it will expand, and if it expands adiabatically without condensation, then it will cool at the rate of around 9.81 Kelvin per kilometer. So, the air parcel which is the upper layer of this 1 kilometer depth, its temperature will be much larger than the surrounding, which is going at 20 Kelvin per kilometer, and therefore, it will be very light compared to the surroundings, it will keep going up. So, this is an unstable situation. Any small displacement of the parcel will allow the parcel to keep moving, and it sets up convection. So, what it says is that the temperature gradient induced by radiative equilibrium in the Earth's atmosphere is so steep that it will induce instability and convection, and this will reduce the temperature gradient, the absolute value, below 9.8 Kelvin per kilometer. Whereas above 9.8 or 10, it will come below that. This is if the atmosphere is dry. But Earth's atmosphere is not dry, it is moist, contains water vapor. So, as soon as the air parcel rises and cools, the relative humidity in the parcel will approach 100% very soon, and by the time it reaches 1 kilometer, that water vapor will condense. And if it condenses, it releases heat. So, the temperature in the height, instead of being 9.81, it will be lower. So, this is called the moist adiabat. So, if the water vapor condenses in the parcel, then the process is not dry adiabatic, but moist adiabatic, and in a moist adiabatic process, the temperature rise of the parcel with height will be slower than adiabatic, and it can be anywhere from 5 degree Kelvin per kilometer to 9.81 when it is dry. So, this is when it is dry and when it is very moist. So, what is observed in practice in the Earth's atmosphere is, especially in the tropics, is in the lowest layer troposphere, the typical decline is 6.5 Kelvin per kilometer. Vary between 6 and 7, but typically 6.5. So, what happens is radiative processes determine the initial temperature variation, and that is of the order of 10 to 20 Kelvin per kilometer. This is very unstable, and atmosphere ultimately starts mixing, and on mixing the temperature profile which is established is either dry adiabatic if there is no moisture, or moist adiabatic when there is moisture, and the observed value is more like 6.5 Kelvin per kilometer. So, this phenomena where radiation creates a high gradient, but that high gradient is reduced due to vertical mixing in the atmosphere by convection, both dry and moist, is called the radiative convective equilibrium. So, finally, the temperature profile in the stratosphere is driven both by radiation and by convection. They cannot be separated. One sets up the gradient, and that gradient happens to be high, and then the convection takes over, and depending on the amount of moist atmosphere will reduce it to around 6 to 7 Kelvin per kilometer. But once you go above the troposphere, there is no moisture there hardly, and there is ozone additionally. So, above the tropopause in the stratosphere, there is no convection, because in the stratosphere, because of the presence of ozone, the temperature does not decrease, it increases with height. So, this is a stable layer. So, in this stable layer, convection is absent. So, we can apply what we learned about radiative equilibrium. Well, here in the troposphere, you have to talk about radiative convective equilibrium. So, above tropopause you have radiative equilibrium, and below tropopause you have radiative convective equilibrium. And so, we start with rate transit equation, we calculate the temperature variation and the temperature gradient, we find it very large, and the atmosphere is bound to be unstable to vertical mixing. So, ultimately we let these layers mix and then find what is the mean variation, and that comes close to 6.5 Kelvin per kilometer due to the presence of moisture in the Earth's atmosphere. But in the stratosphere, we do not have to worry about convection, because it is a very stable layer, because temperature increases height because of ozone being present here. Presence of ozone sets up a reverse gradient there, an inversion layer, and that layer is very stable, and hence you get the radiative equilibrium. So, what you find is that the final explanation for the various temperature height in the Earth's atmosphere has to invoke both radiation and convection in the troposphere, and on the other hand it can manage with radiation alone in the stratosphere. And the analysis we had done just now was for grey gas, but as all of you are aware and we have highlighted many times, strictly speaking you cannot use a grey gas model as atmosphere. So, strictly speaking you have to look at spectral variation of radiative flux with height, and then integrate over all wavelength, and this is the quantity which has to be set equal to 0 for radiative equilibrium. So, in doing spectral variation you have to account for absorption coefficient of carbon dioxide, water vapor, ozone, methane, nitrous oxide, ammonia, all these gases which are present, all these have to be accounted for. All the spectral bands have to be incorporated in this spectral radiative flux, and so this is a very tedious procedure, and this is done usually by large computer programs which are now readily available, and the final result we get is not very different, because in the troposphere finally what is established is the temperature profile determined by mixing in the troposphere. So, although the radiative flux and the temperature gradient we will get by doing the full spectral integration will be different from what we got for gray gas, but finally it is convection which is determining the tropospheric temperature profile. So, finally it will lead to very close to 6 to 7 kilometer, and it would not matter how the grain was set up. But in the stratosphere, of course, it is very important to take into account the role of ozone, because in the stratosphere ozone is the dominant gas which absorbs radiation. And so, what you find is that in the Earth atmosphere radiation plays a complex role along with convection to set up a certain gradient in the troposphere and a different gradient in the stratosphere. Thank you.